Okay, I hope the my slides are visible and I'm audible.
Yes, perfect. Coming across.
All good,
Go
good,
ahead.
sir. Yeah.
Okay. Thank you. So good evening, everyone, and thank you, Rahul and Chetan, for the kind introduction. So today I'm very excited to present an overview of how we can design and implement efficient circuits and systems for next generation cryptographic algorithms focusing on low power embedded applications. So I will start with some background on the current challenges that we are facing in securing embedded devices, for example, in the context of the Internet of Things or IoT. And then I will also discuss the motivation behind trying to solve some of these problems through efficient hardware. And I will give a quick introduction to cryptography in the context of embedded devices and the implementation challenges. And finally, I will discuss some specific examples of efficient hardware implementations of complex cryptographic algorithms. So let's start with the internet or the growth of the internet. And the internet is considered one of the most important technological innovations that has transformed our lives in recent times. And it is increasingly affecting our day-to-day lives. And we have pretty much everything that we use today, all the electronic devices, they are connected to the internet. And a large proportion of these devices are actually embedded systems. And the number of such devices has been steadily increasing thanks to advances in computer hardware and integrated circuit technology. So we now have electronic components embedded in pretty much everything. So here, if we can see, we started with servers and personal computers, then we had laptops, and now we have tablets, phones, smart monitors, smart appliances, even our cars. Everything is connected. And this is really the vision of the Internet of Things, where different devices, they are connected, they collect data, process data, and enable many novel applications. But it's not enough to just connect these devices. The big question today is whether they're secure. And unfortunately, we see a lot of IoT security issues. These are some of the recent IoT security issues in the recent past. There have been proof of concept demonstrations of remotely hacking cars, and medical devices like pacemakers and insulin pumps have had security vulnerabilities. And smart home appliances, again, there have been several cases of security issues. And there are also large-scale attacks like botnet attacks, where like hundreds to thousands of such IoT devices with different kinds of security vulnerabilities are used to launch large attacks on different kinds of internet infrastructure. And several surveys have revealed that commercial IoT products tend to have different kinds of security issues. And this leads to another question, that why is it so difficult to secure the IoT? Why is it so challenging? So of course we have cryptographic protocols, standard security protocols, which are used for securing the traditional internet communications. However, a similar approach, it seems we cannot directly use in the case of IoT because of some unique challenges in the IoT or embedded space. The first and most important would be resource constraints. So many of these devices are small scale microprocessors, microcontrollers with limited memory, limited computational power, and they're also battery powered, which means there is energy constraint. So this makes it extremely difficult to implement computationally expensive cryptographic algorithms on such devices. And particularly unique concern with IoT devices or embedded devices security is physical attacks. So these devices are easier to access physically by attackers, and hence secret information can be extracted from them, also known as side channel attacks. And I will talk briefly about this later. And finally, just the massive scale of these networks with so many devices connected makes it quite challenging to enable efficient key management, especially with the storage limitations on embedded devices and also the limited computational power. And this also means that many commercial devices tend to have pre-programmed keys and also avoid key refresh and authentication mechanisms to get around these constraints. which definitely leads to severe security concerns. So in terms of solutions, of course, there can be multiple different ways of trying to tackle these problems. But our approach is security through efficient hardware. And so this solution still is very closely tied to cryptographic protocols, because strong security guarantees of these protocols make them ideal for securing communication networks, both for the traditional internet as well as for the IoT and embedded space. What's new is that the implementation and design of these systems have to be looked at in a different way. So we have resource constrained embedded devices, which means we have constraints in terms of power, in terms of energy, memory usage, and also the need to secure against physical attacks. And our approach is to unify circuits, algorithms, architectures, and in general, both software as well as hardware, so that we can build hardware, security hardware, which is efficient as well as secure. And I will give some specific examples of such designs. But before that, I will start with some quick overview of what is cryptography, and what are the challenges, and what are the kinds of computations that may be involved. And cryptography, generally, if we talk about cryptography, the first thing that comes in mind is encryption. So if we have two devices, or say one IoT device which wants to talk to another IoT device, or even a server, then we want the communication between them to be confidential, meaning even if it goes through an untrusted network, other devices should not be able to access the data that is being transmitted. And this is ensured by secret key cryptography, which includes encryption, hash functions, and the standard functions are, for example, AES and SHA. But this requires some kind of shared secret key on both ends. So in this example, for like the IoT node and the cloud server, they need a shared key. So how do we establish this shared key? These two devices may be thousands of kilometers apart, maybe at two different parts of the world. And we also want to refresh these keys from time to time for security reasons. And this is where we enter the world of public key cryptography, which involves very complicated mathematical structures, which enables some novel cryptographic protocols like key exchange and signatures that allow two parties or two devices physically located at very different locations to authenticate themselves, and then to establish such shared keys even while communicating over untrusted channel. And for this, we have public key algorithms, for example, RSA and elliptic curves. And I will also, towards the later part of this talk, I will also discuss some other alternatives that are coming up. And these public key cryptography primitives are their security is based on the intractability of some complex mathematical problems, and which means that implementing them is also a challenge. And we'll see how that affects the overall system. So let us take an example of the transport layer security protocol. So if we use our email or even our banking sites, or pretty much any secure communications that we do day to day, it uses HTTPS. So HTTPS is HTTP secure, and it uses this transport layer security protocol to secure the communications. What it does under the hood is just set up a confidential channel between authenticated endpoints using a mix of secret key and public key cryptography. And this typically happens in two phases. I will skip the details, but at a very high level, this happens in two phases. Phase one is called handshake, where the two communicating parties, they authenticate themselves. So they verify each other's digital identities using some complex public key cryptography. And then they do some key exchange to set up the encryption keys, again using public key cryptography. And once the secure channel is established, then they can use these encryption keys to exchange data while maintaining confidentiality. So this is the phase two, or application data phase. Now, if we look at a session, so a session is where two devices perform a handshake, and then they keep on using the newly established keys to exchange encrypted data. So typically, as one TLS session will involve one key establishment at the very beginning, one handshake, and this is followed by several exchanges of data encrypted using the uh, established key. So the handshake part is just at the beginning, and then the rest of the time is just the phase two or application data. And the application can decide when to do another handshake and start a new session with fresh keys. So if we look at this, then it may seem that, okay, we are doing handshake just once. Why do we care about public key cryptography? Let it be expensive. So this is some analysis that we did. So how does the handshake computation energy compare with the total computation energy in a TLS session over while we vary the session duration, data rates, and different other factors? And we can see that the handshake computation actually accounts for, if you look at small sessions, say around a week or so, then it accounts for almost 90 to 95% of the total computation. And even if we do handshakes, say once a year, which is definitely not practical, we should refresh our keys much more often. So even then, handshake energy is around 50 to 60%. So public key cryptography is extremely expensive. So even if we are doing it once per session, it does cost a lot. And so all of these experiments were performed using some embedded microcontrollers while using software. And this really motivates the need for efficient hardware for such public key algorithms. A different way of looking at this energy consumption of different kinds of processing that is happening in an IoT node. So here first we have the radio. Now depending on the communication protocol, the radio energy will be different. RFIDs will have low energy. If we go for Bluetooth, or even if we go for say Wi-Fi, things will change. And here we have the processor just doing some standard benchmarks, and this is where the energy lies. And this is secret key crypto, which is basically say encryption. And here you have public key crypto, again both in software. So public key crypto is several orders of magnitude more expensive than secret key crypto. And what do we achieve with hardware acceleration? We can both secret key and public key, we can bring them down by 3 to 5 orders of magnitude, and now they are really they are even lower than some of the radio protocols energy consumption, which is what we desire. We don't want to spend all the energy on just encrypting and authenticating the channel. So using hardware acceleration, we can achieve orders of magnitude improvement in the cryptographic processing. And I will soon give some examples. But before that, is it enough to have efficiency? At least in the IoT scenario, that's not true. So we also have some unique implementation level security challenges. So we are building hardware for security, but we also need to secure that hardware itself. And this is where we enter the world of physical attacks or side channel attacks. If we are having some encryption or authentication algorithm running inside a chip, then it is operating or it is computing over some secret data. And it turns out that the power consumption or the timing or even the electromagnetic emanations out of this chip, they have a correlation with the secret data that is being computed upon. And attackers can recover the secret information through repeated measurements and experiments. And many of these attacks do not require sophisticated equipment. Just with a reasonable speed oscilloscope and some current probes, we can do many different kinds of side channel attacks. And this means that we need hardware for cryptography, which is not only efficient, but also secure against such side channel attacks. So putting it all together, what are the design considerations for hardware-based security? The first four in the top row, these are the standard ones that we maintain for any kind of digital system design, We want to have low power, low energy, preferably low to medium area, because area translates to how much logic gates, how much memory we are putting on the chip, and this translates to cost. And then performance, although IoT devices, at least the resource constrained low power ones, we don't have a lot of performance requirements, but at least we should not have too much latency in performing encryption authentication. So these are some of the design considerations that we can definitely play with. And now we have some more points added. We have security. The system should be secure, and we should implement algorithms which are secure. We need side channel resilience. So we should be able to prevent at least certain level of side channel attacks. And also good to have some flexibility in the design. This again I will discuss when I give some of the examples. So because there are a lot of security standards out there, lot of options, different ciphers, different public key algorithms, different parameters which give different levels of security. So if we have hardware which can support multiple options, then it definitely becomes an attractive design that we can just use in many different applications. So in terms of design methodology, of course, we can always do general purpose software on a microprocessor, where we will have reasonable performance, but the energy consumption is high, because general purpose processors are just not equipped to handle such complex and computations that are happening, that we require in cryptographic algorithms. And then the other option might be to use FPGAs, which is reconfigurable hardware, where again we have the flexibility of putting different hardware components. We can update the hardware, but then energy and performance are better than microprocessor, but not great. And then the most specialized option would be to design application-specific integrated circuits, or ASICs, where we can really push the performance and also reduce energy consumption. But of course, we lose the flexibility over there. So once it has been programmed, or once it has been fabricated with a certain functionality in mind, then we really cannot do much if with that specific circuit. So what the examples that I will give, we try to take sort of a middle route, where we have both general purpose microprocessor as well as cryptographic coprocessor, which is more like an application specific processor, where different instructions are there in the coprocessor and we can program that. And of course, we can use the flexibility of the general purpose microprocessor, which the embedded system will anyway have. So this helps us achieve energy efficiency along with the flexibility. So I will give 3 examples next on examples of how we can design energy efficient hardware for cryptography. I will start with elliptic curve cryptography, which is the current standard. And so the transport layer security protocol that I talked about, it uses elliptic curves very heavily. Then I will talk very briefly about something called pairings, which are an extension of elliptic curves. And then finally, I will spend some time on lattice-based cryptography. So many of you may have heard about post-quantum cryptography or quantum secure cryptography. So this lattice-based crypto falls in that category. And so this is really the next generation, or something that is coming up or will come up in the next few years. And I will spend some time describing what it is and how we can implement them. So this is mostly, I will cover some of the chip designs that I worked on as part of my PhD.
So we can't hear you. Also, you are not audible.
He may not be able to hear us either. Chetan, we may have to give him a call.
Yeah, let me give him a call. Yes, I just talked to him. It seems there is some network issue. He's trying to reach me. Rahul, can you hear me?
Yes, we can.
Yeah. Okay. So he will rejoin. He said. Let's see. Participants can post their question into the chat window. Any question?
Utsav, I see that you're back, but we can't hear you as yet.
Yeah, sorry about that. Some network issue. Really sorry. Am I audible now?
Yes.
Yes, you are.
Okay. I will restart from here. Okay. Yeah, my apologies for the delay. So I will go over three examples of the efficient crypto hardware design. So the first one would be on the current standard, which is transport layer security, which I explained in some of the previous slides. So we tried implementing the standard transport layer security protocol on some embedded microcontrollers. And the challenges that we faced were mainly in the energy consumption and the memory usage. So when we implemented TLS in software, it was the handshake itself was consuming around 30 millijoules of energy. And if we looked at the code size of this software implementation, it was around 90 kilobytes. So which is really large for many of the embedded microcontrollers, which will probably have 64 to 128 KB memory. And we also need to have reserved space for the application software. And this is where we introduce some hardware accelerators into the system. So energy efficient accelerators for the cryptographic algorithms as well as for the TLS protocol itself. And we were able to reduce the energy consumption down to 70 microjoules. And the code size went down to around 10 kilobytes. So of course, this was at the cost of additional logic, which we had to add, and which means that the protocol was sort of put into the silicon itself. But TLS protocol is standard. These kinds of protocols, they are changed maybe every 10-15 years. So it makes sense to have such a protocol in the dedicated protocol engine in the hardware itself. So this was the first design to accelerate the complete protocol. And elliptic curve cryptography accounts for about 99% of the handshake computation cost in TLS. And it involves arithmetic with very large integers. And at a very high level, elliptic curve cryptography involves, like this is an elliptic curve, very simple example. And we deal with points on the elliptic curve. So the input is one point and a scalar, and the output is another point. And again, without going into the math, the operations can be broken down into basic modular arithmetic operations like modular addition, subtraction, multiplication, inversion. And 128-bit security level is the standard for which we use 256-bit primes, which means we are dealing with all these arithmetic will be with 256-bit large numbers. So we designed a configurable prime field ECC hardware where we could perform ECC computations over different kinds of elliptic curves and up to 256 bits. So if we want to scale down the security a little bit, we can always do that by using slightly smaller numbers like 192 or 160 bits. And then with different optimizations at the circuit level, algorithm, as well as architecture level, we were able to reduce the energy consumption of the basic ECC operations. And these are some measured results from the system that we designed. So the curve size is basically the size of the prime field. So here we have 256-bit, 224, 192, and 160. So it offers very nice scalability in terms of security versus energy consumption. So if we require more security, we can always go for larger primes at the cost of higher energy consumption. And if we are okay with, if we are really constrained in terms of energy, then we can scale down the security a little bit. And then we can do that by using smaller primes. And this was the overall architecture where we integrated these crypto accelerators with a dedicated state machine which can perform the TLS protocol. So it can do the handshake as well as the encryption, authentication, all of that in a single piece of hardware. And again, we observed around 2 orders of magnitude reduction in the latency as well as the energy consumption compared to full software. And also the code size went down by several tens of kilobytes. And we also put this into a system demo where an IoT node, we sort of emulated an IoT node on this chip, and it was connected to some temperature sensors and accelerometers, and it was sending encrypted data through a Raspberry Pi to a PC, and it performed this TLS handshake, and then it was sending encrypted data. So even if an attacker sits on this gateway, it will not be able to decrypt the data that is being sent. And this was the test chip, and we included some side channel countermeasures. So the basic ones in public key cryptography are timing and simple power analysis attacks, where by just looking at the power consumption waveforms, or ideally one measurement, or if not, maybe few measurements, we can try to figure out the secret key. And we had countermeasures against such attacks. And also for more sophisticated statistical attacks, we included some randomization-based countermeasures. So again, some more flexibility here. If we want to protect against such statistical attacks, we can turn on the scalar randomization at the cost of increased energy consumption. And because we had a processor and this accelerator, we were also able to implement different other protocols on this system as well. And a small extension of this elliptic curve based cryptography. So we have something called pairing based cryptography. Right now, this is very popular in the context of blockchain and zero knowledge proofs, which come as part of many of the blockchain protocols. So we did not implement blockchain, but we implemented something called signature aggregation, where which can reduce the communication cost in blockchain networks. And we also implemented some basic level of secure computation on encrypted data using functional encryption. So again, I will not go into the mathematical details, but what functional encryption does is we can send encrypted data, and then while decrypting, we don't get the data itself, but we get a function of the data. So we were able to run some basic classifiers on the encrypted data using this kind of setup. And I think I'll skip this. So again, we had some hardware architecture for supporting the pairing based. So pairing based or pairing friendly elliptic curves, again, these are even larger primes. We had 381-bit prime fields and more complicated operations, which I will not go into the details of. So we had some hierarchical architecture for performing these kinds of operations. And this was, again, the test chip. And protocol, in terms of evaluating different protocols, again, we were able to observe about two orders of magnitude reduction in energy consumption compared to software. And once again, we also had SPA, simple power analysis, and differential power analysis countermeasures. And one thing to note here is that these side channel countermeasures, they also come at a cost. They are not really free. So as we add on more countermeasures, we pay slightly in terms of energy consumption. And the last design I will talk about is on lattice-based cryptography. So as I said, this is part of the worldwide effort on post-quantum or quantum secure cryptography implementation. So there's a lot of advances in the field of quantum computing recently. Large-scale quantum computers are being envisioned. And it so happens that the public key cryptography that we have today can be broken using quantum attacks, not at the moment, but when we have really large-scale quantum computers, it can be done using Shor's algorithm. So different standards bodies have already started working on post-quantum or quantum secure cryptography, or alternatives to the current public key infrastructure. And the most promising candidate here is lattice-based cryptography. I think I have a little bit of time, so I will quickly go over what is lattice and what this is about. So this is quite different from the elliptic curves and the geometrical kind of representations. So lattices are basically integer linear combinations of basis vectors. So this is a 2D lattice. We have two basis vectors b1 and b2, and the lattice can be generated by just taking linear combinations of b1, b2, which are these green points here. And there are some well-known hard mathematical problems related to lattices. For example, the shortest vector problem, which is to find the shortest vector in the lattice, and also the closest vector problem. So given any point in space, we need to find the closest lattice point. And of course, these seem trivial with the small 2D lattice, but if we scale up that lattice dimension, say, so this is a 2-dimensional lattice. Suppose we scale it up to a few hundred or maybe 1,000-dimensional lattice, then the complexity of solving these problems grows exponentially. And if we look at the best known algorithms, both classical as well as quantum, there is no algorithm which can break this. There is no attack which can break like SVP or CVP in polynomial time. And this is the foundation of security of lattice-based cryptography. And again, I will give some toy examples of what we really do, what are the computations in lattice-based cryptography. So we don't use SVP and CVP directly. We use something called learning with errors. This is a very well-known problem in the machine learning field, which has nicely integrated itself into cryptography as well. So this is a toy example. Say we have a matrix A, a vector S, and another vector B. So we know A and we know B, and we need to find S. So B is the product of A and S. So this is easy. We can find this using Gaussian elimination. What learning with errors is about is what if we add an error vector to this term? So instead of AS, we take AS plus E, where we do not know the elements of this vector E. So it turns out that if the matrices and vectors are large enough, and the elements of S and E are drawn from certain very specifically chosen probability distributions, then this problem is very hard. And this is the underlying the theory of the LWE problem. Of course, we would want to scale it to much higher, larger matrices if we want to use it for cryptographic protocols. And if we are dealing with matrices, then of course our storage is quadratic and our computation is roughly cubic. So this is a lot of overhead if we want to use LWE. So there are some alternatives. The first one is ring LWE, where instead of taking a full matrix, we go with like a circulant matrix, where those are shifted versions of each other, which means it is okay to just store the first row. Like this, then the matrix multiplication can be, it can be proven that this can be converted into a circular convolution. And the moment we hear convolution, we can do something similar to a Fourier transform. So our computation is now logarithmic or n log n. We don't do Fourier transform, we do something called a number theoretic transform because we are not dealing with complex numbers here. And finally, we have something called module LWE, where we take a matrix of circular matrices. So it's somewhere in between LWE and ring LWE. So in terms of computational requirements, we have to generate these elements from certain discrete probability distributions. And we have to do these matrix vector polynomial operations and also these transforms so that we can do this polynomial multiplications. So if you look at the implementation cost, then most of the energy goes into sampling or generating these elements from different probability distributions. And the area or the cost of implementation goes into the memory that is required for performing all these different transforms and storing these matrices and vectors. So basically, then we need an energy efficient circuit which can do this sampling or generation of these elements, and an area efficient architecture for performing the transforms of these matrices and vectors. So we use certain architectural techniques to reduce the energy consumption and also some algorithmic optimizations to reduce the energy consumption of the sampler. And again, we went back to the early days of FFT hardware, and we were able to take some derivatives of certain constant geometry architectures for Fourier transform. And using that, we were able to achieve around 30% area savings without any loss in throughput. I'll skip this. And so again, very configurable and flexible architecture is what we designed, where we can put these kinds of matrices, vectors, and polynomials, and configure them with different parameters, different primes, and different sizes. And this would help give us the flexibility to program them as we want, and then implement different kinds of protocols. This is the test chip, and yeah. So the National Institute of Standards and Technology is the US NIST. They drive many of these standardization efforts in the field of cryptography, and rest of the world, we have very strong confidence in their analysis. So they started this NIST PQC, or post-quantum cryptography standardization, very open effort where researchers from academia and industry, they joined hands, they proposed different algorithms and then different implementations. So we evaluated multiple such schemes, both key exchange as well as signatures. Again, doing some software hardware co-design. The most complex operations were happening in the hardware accelerator and the remaining in software. And again, we were able to get order of magnitude improvement in energy efficiency and performance. And also we had different kinds of side channel countermeasures. I will skip that in the interest of time. So this brings me towards the end of my talk. So to summarize, domain-specific hardware is very important for embedded security. We are looking at a new wave of domain-specific hardware designs for machine learning, for bioinformatics, for different other applications. So cryptography is also another application where we really need efficient application-specific circuits and architectures. And we need to co-optimize or co-design algorithms and architectures based on the implementation platform. We should relook at the algorithms and try to optimize them. Side channel countermeasures are very important. We need to protect these implementations, these devices against physical attacks. And finally, it's always great to have a flexible design with configurable parameters so that we can support different kinds of cryptographic algorithms and protocols. So this the NIST post-quantum standardization. So when we worked on this on the chip design, that was back in end of 2018. So the standardization process had just started. So NIST announced the first set of algorithms on 5th July last year, and the primary recommendations were Kyber and dilithium, which are lattice-based, and our design was supporting it. It still supports because of its flexible architecture. It can support both of them. So I think this was nice that we were able to contribute to this effort in certain way. And post-quantum cryptography is very big right now. A lot of different directions are being pursued. So if you are interested in learning more about post-quantum cryptography without going into too much of the complicated math, so along with my collaborator Sujoy Sinara from Austria, we together wrote this tutorial paper recently. So feel free to go through it, and if you have any comments, it will be great to discuss. So to conclude, I think if you look at history, then cybersecurity has been strongly influenced by hardware. If you look at the World War time, the Enigma code was broken by the Bomba machines, which were some of the first electromechanical computers. And then the data encryption standard was cryptanalyzed using probably the first application-specific like ASIC clusters designed for cryptanalysis. Custom chips were designed for breaking the codes. And while breaking the code may sound destructive, but it always leads to new innovations in building more robust and resilient encryption authentication algorithms. So we can only imagine what will be next. So it was 1941, 1998. We are probably looking at many new innovations that will be driven by hardware, which will be like hardware-driven innovations through circuits and systems in the field of security. These are some of the ongoing research directions right now in my research group at ISC. So we are definitely looking at quantum secure cryptography, different efficient implementation, side channels, and also trying to look at some of the new algorithms. There is a new standard process starting on the signature side, so definitely very interesting. And we are very actively working on hardware for computation and encrypted data. We are looking at
So
fully
yes,
homomorphic encryption.
your slide is not changing, it seems. Still we
Uh,
are at continuing the, okay, yes, now it is changed. Yes.
oh, okay,
Yeah.
okay. So we are looking at fully homomorphic encryption, which is like the holy grail of encryption, where we can perform, at least theoretically, arbitrary computations in the encrypted domain. But that involves very, very complex computations, and hardware is going to be absolutely necessary for enabling such applications. And then finally, we are looking at how we can use some of the emerging technologies like processing and memory or novel devices in the field of security, also experimenting a little bit on the quantum side of things. So with that, I end my talk. So thank you. And this is my email and website. And I would like to thank Chetan, Ayan, Rahul, and everyone in the IEEE Bangalore chapter for inviting me. And I'll be happy to take questions. Thank you. And again, sorry for the network glitch between.
No, it's a great talk, Utsav, and we have a couple of questions. I'll read out from the chat window. Meanwhile, I also encourage other participants, if they have any question, please put it into the chat window and I'll read out them for you. So one first question is from Dr. Vijay Kumar. Which software and hardware? I think he's trying to ask hardware software code designed probably from your first chip. That's what I could infer from this single statement. Can you just comment on that? Which part you have done with software, which part you have done in hardware?
Okay, okay. So in the transport layer security, we actually had all three flavors, because we had the TLS accelerator, and then we had the individual crypto accelerators, and these were integrated with the RISC-V processor. So here we could, so yeah, this is where we show this. So we can do full software. So we were using Mbed TLS, which is an open source TLS implementation. And then this orange bar is where we were doing just the encryption, authentication, just the crypto primitives in software, but the protocol scheduling and other operations were being done in, the crypto operations in hardware and the protocol in software. And the green one is where everything is in hardware. Just the software is just sending in data and then waiting for the computation and then reading it back. So all three flavors we had here. And in the later ones, we did not have the green, even in the pairing we had sort of, in the lattice-based crypto, we went with this software plus hardware, because not everything was in software.
All right, so we have another question from Anushka. If public key cryptography has the issues of high energy consumption and being penetrable by quantum attacks, why is it being used? What are its advantages over secret key cryptography, which intuitively seems more secure? So that's the question.
Okay, yeah, that's a great question. So why we need public key cryptography? So as I said, we can do secret key cryptography. It's fine if we just want to do encryption with the same key over and over again, but we need some mechanisms to update these keys. Also, suppose we have different devices they want to communicate, they would like to authenticate each other. So for example, when we say enter our office, or we have to do some kind of say biometric, or we have a card based entry, so it is authenticating that this is the right person. Similarly, devices would also like to authenticate each other. So this is not possible using secret key cryptography. So this is where we would want to use public key cryptography. And it is possible, but not as robust as using public key. So that is why we would like to use public key cryptography. Also, some of these computation and encrypted data and other applications, that is definitely very unique to public key only. And public key is vulnerable to quantum. Secret key is also vulnerable to quantum, but using Grover's algorithm. But we can sort of deal with that by increasing the size of the keys, but it's not as easy in public key. But that is, I think, even though current public key is vulnerable to quantum, we are having very nice alternatives like lattices. Lattices, although they are not only quantum secure, they are also in a way more efficient than elliptic curves. So I think that's an added advantage.
Okay, great. There is another question from Shutao Jahan. Is there still some challenges in the hardware design for elliptic curve cryptography?
Right. Definitely, I think although a lot of focus has shifted towards lattices and post-quantum, we would definitely, we will be using elliptic curves for quite some time. So for example, Google has, on an experimental basis, they have rolled out some of these implementations of the OpenSSL, where they have included both elliptic curve as well as lattice. So it's a hybrid kind of key exchange authentication. So for quite some time, we will have both elliptic curves as well as lattices. So I think there is a lot of value in still working on elliptic curves. There are new elliptic curves that are being designed. We looked at the NIST standard curves, which were proposed some 10 years back. But there are new curves like curve 25519, ED448, and some others as well, which have nice properties. Like they have efficient to implement, but then there are some side channel, nice side channel properties as well.
Okay. There's one more question from the same participant is what is the bottleneck of current hardware design for SHA-3 and NTT in lattice-based cryptographies?
Okay. So if we look at, so first let me address the SHA-3 part. So if you look at how SHA-3 works, it has a big state. It takes a 300-bit state, and then the input comes and it goes through different nonlinear operations and different permutations inside the SHA-3 function. So if we use, say, our general purpose processors for doing these functions, it is not efficient. So it's not simple AND or XOR. So each operation will probably be broken down into 10 different instructions in the general purpose scenario. So if we build dedicated hardware for it, will become much more efficient. And similar case for entity as well. Entity, it involves modular arithmetic. So it is very much like FFT. It will go there. So it is very much like the fast Fourier transform, except all the operations are done in finite fields. So we have a butterfly very similar to FFT, but all the arithmetic is modular arithmetic. So again, if you want to do modular arithmetic using our general purpose processor, then multiple instructions will be needed. And it has to go back and forth between the register and memory. And similarly, when the transform itself is happening, each butterfly operation takes three inputs and two outputs, including the twiddle factor. So then all of this data movement and all will add on to the cost.
So there's one more question from Shashidhara. What possibilities the security can be explored in emerging devices like memristors or MEM devices?
Right. So very good question. So if we look at memristors, of course, on the machine learning side, there is a lot of exciting work happening like in memory using memristors and matrix computations. Some of them can possibly be extended on the crypto side as well, because like here in lattices, we are doing some polynomial matrix kind of operations. But there is a very fundamental difference between the two. So if we are looking at machine learning applications, they are resilient to errors. So we are okay with having some errors, and we can even do some analog computations. That becomes a challenge in cryptography because we want everything to be exactly the same. Even one bit changes, and our protocol will not work. So I think that gives some interesting directions. And also there is some work, there is some literature on using these memristor kind of devices for random number generation or for physically unclonable functions as fingerprints for electronic devices.
Very interesting. So Rahul, can I have a few more minutes or should we stop at 8? Because there are...
We can take a couple of more minutes.
Sure. Okay. So there is a question from Rajeshri, whether elliptic curves is possible over quantum cryptography.
Okay. So the elliptic curve operations that I explained earlier, they are not secure against quantum, but there is an elliptic curve variant of post-quantum cryptography using isogenies, elliptic curve isogenies. They require a special kind of elliptic curves, but they are still under active study. So the super singular isogeny-based key exchange was a NIST candidate, but just few months back it was broken. So they were able to break it using just a very simple laptop. They use it to do some computations and break the encryption. So that is broken, but there are some signatures that are being proposed using isogenies. So there is some elliptic curve alternative, but they are being studied right now.
Okay. So I think there is a question from Rahul.
So what kind of side channel attack countermeasures you have found to be most effective? You mentioned randomization, scalar randomization. But is that the only mechanism that you've used, and are there others which you think are more effective, but you didn't use it for various reasons?
Right. So for the timing and simple power, it is just making things constant time, and so there's no data dependent branching. That is like the bare minimum requirement. And then, of course, randomization or masking is the next step to prevent some of the more complicated attacks. So these are very algorithm specific. So if I have a scalar randomization for a countermeasure, that will be very specific to elliptic curves. It won't apply to, say, lattices. In lattices, we have to look at it in a different way. So these are more algorithm-specific countermeasures. Some generic countermeasures have also been explored in literature, where people have been looking at, say, voltage regulators, how we can include some randomization in that itself, like on-chip voltage regulators, so that if I try to measure the power, I won't be able to even get some of these nice waveforms. So that is we have not looked at those in this work, but that is another parallel direction in this field.
Okay. I would say this is the last question. So Himawati was asking, her research focuses on physical unclonable function. Is it she should concentrate on secret key or public key crypto?
Okay.
I'm not sure it's related. Yeah.
I think there is not much. I think there is no as such restriction on using which crypto to use, because the puff would give you some kind of key to use, and that you can use in either way. I mean, there are protocols. If you are looking at very low overhead protocols, you may go with secret key crypto using some hash functions, but they can easily be extended to public key cryptography as well.
Okay, one last question from Manushka. During cryptanalysis, as mentioned in one of the last few slides, what are the metrics to determine the reliability resilience of a cryptographic algorithms, and how is this cryptanalysis done?
Okay, yeah. So there are many of these metrics are actually heuristics based. We do not have proofs. So for example, elliptic curves or even lattices, it's not like we have a concrete proof. Lattices are actually more concrete, but they rely on some computational assumptions, hardness assumptions. So for example, elliptic curve cryptography relies on the elliptic curve discrete logarithm problem. So it is a hard problem which has been analyzed over multiple decades, and algorithms and mathematicians and theoretical experts, they have been looking at it, and it's just that the latest and best algorithm does not break it. So that is how things work. And if you're looking at, so that would be on the public key side. On the secret key side, it is a lot of the cryptanalysis is based on heuristics. So there are different tests where you flip certain bits in the input and then try to look at how the output would behave. And there are very standard cryptanalysis attacks like linear differential and linear cryptanalysis, differential, and other kinds of attacks, which are explored when, say, a new algorithm is proposed. So, lot of probability theory and statistics involved there.
Okay, great. So I think we'll stop here. So Rahul, I may need your help a little bit. So let's thank our speaker again. Thank you so much, Utsav.
Thank you. Thank you.
Yeah. So Rahul, do you have this feedback link with you so we can share with the participants?
The feedback link will go out to the participants subsequent to this.
I see. Okay.
But we do want to take the opportunity to thank Utsav again and share a certificate of appreciation from IEEE CAS.
Thank you.
For this wonderful seminar.
Thank you, Utsav. Thank you, everyone. So maybe we can conclude, Rahul.
Yep. Thank you.
Yeah,
We can
thank
stop
you.
recording.
Yeah.
Thank you.